I knew of him since 1992, when my supervisor at the time, Achim Jung, was actually, well, I wanted to go abroad. I was studying in Germany at the time. So he said, well, you could go to McGill or to Penn. So I sent a letter to both universities, and then I got the reply I got from McGill, must have been the admissions office or something. I said, I'm interested in studying mathematics or computer science and things like that. And they sent me a letter welcoming me to the program in German studies. So that was a narrow miss, and I went to Penn. Then I didn't really meet, but I saw Prakash in 1995 in Cambridge. There was a special year, and I remember still, I didn't know him at the time, but he was giving a talk, filling the blackboard with integrals, and it all looked very brilliant, but we didn't actually meet. And then we finally met in 2000, so of course, as you all know, Prakash knows many things, and as soon as I found out that he also knows physics, I thought this is a wonderful opportunity to get someone to explain quantum mechanics to me, which is something I've always sort of wanted to know, and I figured, an intelligent person can probably learn, but no one had really ever explained to me, so he said, sure. And this is how the conversation went. Please teach me about quantum mechanics. Prakash, do you know about vector spaces and linear maps? Yes? Great, then you already know quantum mechanics. Now, Prakash claims to be born in 1954, but I've always wondered how the man could learn in 60 years what would take me 250 years to learn, since he knows more mathematics than most mathematicians, more computer science than most computer scientists, and more physics than most physicists. But then I was looking through some archives the other day, and I found the answer to this question. I found an old picture of this. Is actually the first Bellairs Quantum Workshop of 1937. There's Prakash right here, and so he's apparently been around a lot longer than he claims.
Before Photoshop was invented.
Alright, so now I will give you a talk. This is actually on a different topic than what the schedule says, but I'm also following other precedents here. In fact, I was lecturing about this at the spring school last week, and Prakash skipped my talk. So, now I have a captive audience because he could not possibly leave. He couldn't even take out his laptop and start checking his email, the poor guy. So, right, so this is about an algorithm in quantum computing. But the lesson from the previous slide applies. If you know about vector spaces and linear maps, then you know everything about quantum computing that you will need to know for this talk, basically. So, in quantum computing there is an important problem where you're given a unitary operator and you wish to approximate it in terms of generators. So you're given some discrete set of unitary matrices, okay, and they span, and you look at the span of those things as a subgroup of, for example, U2 or SO3 or some other such group. And so, of course, if your generators are not completely trivial, then their image will be dense inside of the group, and therefore you can approximate any operator up to epsilon. But it's actually an important practical problem how to do this well, okay? So the standard solution to this algorithm is the Solovay-Kitaev algorithm. It's been around for 19 years. And it's based on geometry, okay? And in fact, a lot of quantum information people learned about things like Lie brackets and Lie algebras and manifolds back in the 90s because of these applications, okay? So these geometric algorithms are based on a very simple idea. If I'm standing on some point on the Earth and I walk 1 meter north, 1 meter east, 1 meter south, and 1 meter west, do I end up at exactly the same spot that I started? Of course not, because the Earth is curved, right? But I end up very, very close, right? So in a nutshell, if you know how to approximate A and B up to epsilon, then you know how to approximate A inverse, B inverse up to epsilon squared. And by just iterating this procedure somehow on the manifold, you can approximate things. That's the idea. So it uses geometry to solve this problem. And I have this thesis here that good algorithms come from good mathematics, so that's certainly an example of that. And now, very interestingly, in the last 2 years, we found another completely different family of algorithms solving this problem much better, in fact, than Solovay-Kitaev. and it's based on computational algebraic number theory. So hopefully a lot of people who work in quantum information theory and other areas of computer science will now learn algebraic number theory, because it turns out to be incredibly useful. And I know that Joel and Ben know this because the sort of problems that they were talking about were also sort of a similar nature. All right. So first, before I tell you what the algorithm actually is, let's just compare. So you want to approximate something up to epsilon, okay? So you can consider how the size of the circuit you get sort of scales as a function of epsilon. And the Solovay-Kitaev algorithm does pretty well. This should be 3.97 in the exponent here. I forgot a pair of curly brackets. Okay. But the point is, so 1 over, log of 1 over epsilon is the number of digits of accuracy that you wish to get, right? And a lower bound is that it's linear in the number of digits, because roughly every time you double the number of gates, you can roughly double the accuracy in principle. Okay, certainly you can't do better than this. But the Solovay-Kitaev algorithm doesn't quite achieve this, so it's approximately a 4th power of whatever would be optimal. So in numbers, you see that these things grow polynomially, but quite much more faster than this lower bound. Okay. So I would like to tell you how we can improve upon this algorithm. Okay. In fact, actually, we will meet the new algorithm will actually achieve the lower bound. Okay. It will actually be optimal, not O of optimal, but literally optimal. Okay. So I will say how that works. And to do that, I will first talk about mathematics. So for the next 15 minutes, it will just be math. Okay. No quantum anything. So here's the sort of object that number theory studies. For example, the ring Z adjoint square root of 2. So that's the smallest subring of the real numbers that contains the square root of 2 and obviously the integers. So the elements in there are all of the form a plus b root 2, when a and b are integers. Of course, that's a ring because you can add, multiply, and subtract such numbers and get another number of the same form. It also has a conjugation operation, which I denote bullet. It works exactly like complex conjugation, except that here we're talking about a root of 2 instead of a root of -1. But other than that, it's the same idea as complex conjugation, right? You just negate the b. Okay. And this map is an automorphism, which means that it's preserved. It preserves addition, multiplication, and subtraction. And finally, let's note that, of course, these numbers in general are irrational, the elements of this ring. However, if you multiply some such number by its own bullet, you always get a rational number. In fact, you always get an integer, because clearly a bullet times a is just equal to a squared minus 2b squared by one of the binomial formulas. Okay, so that's always an integer called the norm of alpha. It's also, so this is the algebraic norm, different from, like, say, a Banach space norm. The only requirement of such a function is that it should be multiplicative. It doesn't have to satisfy a triangle inequality or anything like that. Okay, now how should we think of the ring Z root 2? Certainly we all know that this is dense in the real numbers, because even if you just consider multiples of root 2 and take the modulo 1, right, it's just going to wrap around the unit interval and fill it up fairly quickly. But I will actually tell you that it's sort of wrong to think of this as a dense set. It's much better to think of this as a discrete set. So, by the way, I couldn't decide whether I should draw the real line vertically or horizontally, so I just drew it at 45 degrees. But now we can pull this apart into 2 dimensions. Okay, so I'm still talking about the same points on the number line. So really the point is actually a point on this diagonal. I've just pulled it at a bit of a distance to the number line so we can see better where these points actually are. And of course they form a grid. So here on the x coordinate I've shown the integer a. On the y coordinate I've shown numbers of the form b root 2, where b is an integer. So this is not quite an equally spaced grid, but it's, well, the spacing in the vertical direction is root 2. Okay. And of course every number a plus b root 2 corresponds to a unique point in this grid. And you can sort of see which number it is. For example, where there's positive or negative, or which of 2 is greater, simply by projecting it back onto this diagonal. Now, but this picture now, and then we see that sort of discrete. This picture also explains what the automorphism does that I talked about before, because we can now just project the whole grid onto the opposite diagonal. So if you put a coordinate system here where one is in this direction, then it's just a minus b root 2. Therefore, you can see that you know, you can sort of see what the automorphism does. Takes the point from this line, moves it somewhere in the plane, and then projects it onto the other one. Now, this automorphism is highly non-continuous. This is as non-continuous as a function can get. It actually never happens that A and B are close. It never happens that alpha and beta are close to each other, and alpha bullet and beta bullet are also close to each other. Whenever alpha and beta are very close, alpha bullet and beta bullet will be very far. So it's exactly the opposite of the definition of continuity. Okay. Why is that? The proof is very simple. If you simply multiply this by that, you get an integer. Because I just noticed, we just noticed this before, right? If alpha minus beta is one such number and the bullet is the other number, then you get an integer, right? So the closer these things, and an integer that's not 0 must be at least 1. So if these things are close, then these things must be far, okay? And you can also see that in this picture, because if somehow alpha were close to 0 and alpha bullet were also close to 0, then obviously in the grid it would have to be in some epsilon neighborhood of 0. And it can't because the grid is discrete. Okay, now I want to talk about a class of problems that arises from this automorphism. Consider a subset of the real numbers. Consider an interval of the real numbers, in fact. A closed interval, okay, like this one here from -1 to 1, the green set. Now define the dual grid of this set to be the set of all duals of points that are in here. Now, of course, not every element of this green interval is actually an algebraic integer from the given ring, but certain ones are, and then you can consider the dual of all of them. So then you get something that's discrete. For example, this here is the point 2 plus square root of 2, and that's in the dual because 2 minus square root of 2 is approximately here. It is in the green set. Okay. Now there is a kind of duality here. In fact. It's easy to see that the grid is infinite in both directions. Okay, it's like one of these Penrose tilings. It's not repeating, but it's very, very uniform. There are only certain distances that actually can occur here. In fact, only 3 different distances can occur. So it's infinite in both directions, and it also must be discrete, because we already know these points have distance 2. So the duals of these points must have at least distance 1/2 or something like that. Right? It just comes from the non-continuity of the dual. So that in particular, the dual of something compact is always something discrete, which rather reminds me of the sort of duality you have in between compact groups and discrete groups and things like that. So that's the dual of a set. Now, when you make the set B bigger, the dual also gets bigger because it's a monotone thing, right? There are going to be more points whose dual is in here. And so if I triple the volume of the set B, or the area, the length of the interval B, then the density of the grid will also approximately triple. Okay? And now the grid problem is, given 2 sets A and B, find all the points on the grid of B that are elements of A. So in other words, this intersection here, these 4 points. Find all the B grid points that are elements of A. Let's call that a grid problem. Okay? And the grid problem, so we would like to have an algorithm for solving this grid problem. Okay? And it's not very difficult. In fact, it's useful to sort of reformulate it by looking again at this 2-dimensional picture that I was telling you about before. So remember that the point here, if we wanted to know what it actually is as an element, of Z root 2, you'd have to project it onto this diagonal. So now it has to be an element of a certain interval in this diagonal here, right? That means it has to be between these 2 lines, right? To satisfy the A part of the grid problem, it has to be between these 2 lines. To satisfy the B part of the grid problem, it has to be between these 2 lines, and therefore we're actually really just looking at points from a discrete grid that lie in this little rectangle at 45 degrees. Now it's immediately clear that there's going to be a finite number of solutions. It's also immediately clear that we have a relatively efficient algorithm for finding these solutions, almost. Namely, when A and B are relatively large, this rectangle will be sort of relatively fat, okay? And in that case, the number of solutions scales roughly as the volume of this rectangle. So you can simply find sort of the lowest possible coordinate and the rightest possible coordinate, then you have an integer number of points to check, and for each of them you can find all the grid points, and it's efficient, okay? So the easy case occurs when both A and B are relatively large. However, there is a difficult case which occurs, and that's when one of the two intervals is really, really small. But then you have a very, very long and skinny rectangle. Very, very thin and possibly very long. Right? Think about if this thickness here were, epsilon, where epsilon is really, really small. Then you could imagine that this rectangle may not hit any grid point, right? Or maybe it will hit some grid points, but we can no longer find them by enumerating every possible x-coordinate and simply checking if it intersects this rectangle here, because we would be enumerating many, many points and never find a solution, right? So it would be like looking for a needle in a haystack to actually find grid problems in a long and skinny rectangle. So what is the solution to this problem? This is where algebraic number theory comes in really handy. The solution is something that we can call scaling. So notice the following clever thing, right? The number 1 plus root 2, which I call lambda, is actually a unit of this ring. Because the inverse of 1 plus root 2 is just negative 1 plus root 2. Right? That product is equal to 2 minus 1, which is equal to 1. So both that number and its inverse are integers, are in this ring z root 2. So why is that helpful? Well, 1 plus root 2 is approximately 2.4, so that's a relatively large number, certainly larger than 1. Its inverse is approximately 0.4 or something, and that's a relatively small number. Now, the crucial observation is that if you think about what's a solution to this grid problem here, right? If alpha is in this set and alpha bullet is in that set, now replace the number alpha by lambda times alpha. Then lambda times alpha is an element of the set lambda times A, which is a bigger set. And here you have lambda bullet times alpha bullet is an element of lambda bullet times B, which is a smaller set. So the solutions to the grid problem for A and B are in 1-to-1 correspondence with the solutions to the grid problem for lambda A and lambda bullet B. Lambda bullet is just 1 minus root 2, so that's the negative of lambda inverse in fact. So we can equivalently, without changing the set of solutions in any essential way, we can make one of these sets fatter and the other one smaller. So that means we can reduce the case of a long and skinny rectangle to the case of a short and fat one. Again, I'm going to multiply the A set by lambda, so its width will be multiplied by approximately 2.4, and I multiply the B set by effectively lambda inverse, or lambda bullet, right? And then the long and skinny set becomes a short and fat set, but the solutions are in 1-to-1 correspondence because you can undo this. Right? You can multiply again by lambda inverse and go back to the original set. So here we have 3 solutions, 1, 2, 3, and you can just check if I drew the slide correctly. These correspond to these 3 solutions, 1, 2, 3, and 1 near miss, by the way, but that's not a solution. And then you find, in fact, 1, 2, 3 solutions here. They're here, here, and here. If you can see that from the back, you probably can't. Okay? So therefore we have an algorithm which will always efficiently find all solutions to the grid problem, even if one interval is very small. So I just described more or less the algorithm, right?
Is lambda the only unit? So
lambda is
aside from 1 and minus 1?
So lambda and minus 1 are the generate all the units.
All the units.
Lambda minus 1 are generators for the multiplicative group of units. There are lots of theorems about that. If you have an algebraic field, you have the ring of algebraic integers in it. There's a theorem that tells you can count the units basically by looking at the number of whatever. There are theorems about that. You count the number of homomorphisms of that field into the complex numbers.
Oh, yeah.
And if there are n real ones and m complex ones, then I think you get n plus 2m units or something like that. All right. So this is, by the way, this mathematics is 200 years old, right? I mean, Gauss knew all of these things, and it was all worked out in the 1840s by someone called Kummer, and even Fermat before that, did. So this is not new mathematics, right? But it's sort of new algorithms, in a sense. And now I want to tell you what I really want to do, which is to solve 2-dimensional grid problems. So 2-dimensional means it's a subset of the complex numbers instead of the real numbers. So here we consider a slightly different ring, Z omega, where omega is a 8th root of unity. An 8th root of unity is something on the unit circle at 45 degrees. So that's related to the root of 2 also, because that's equal to 1 plus I over root 2. Right? So in fact, if you intersect this with the real numbers, you get just Z root 2. same ring that we previously talked about. So let B be a bounded convex subset of the plane, then we will define its grid to be the set of all complex numbers that are whose dual is in the set B. Okay. This ring also has an automorphism because you can just map omega to negative omega. It's the same as mapping root 2 to negative root 2. Okay. So here's the grid of a little square, for example. You can see that it has a nice 90-degree symmetry, as a grid of a square should, right? Here, if I make it bigger, for example, make it a circle, the grid also gets bigger and denser, in other words. And now it has a 45-degree symmetry, because the circle obviously has a 45-degree symmetry, or any degree, but the ring has a 45-degree symmetry, so that's actually rotationally invariant now under 45 degrees, this grid. But now you have more interesting cases, like your convex set could be, an ellipse or something. And then the grid maybe would be denser in one direction and less dense in the other direction. And the two-dimensional grid problem is analogous to the one-dimensional one. So given two convex subsets of the plane, find all the grid points of the green set that are elements of the red set. And in this example, there would be 7 solutions. Okay? Now there are easy cases and hard cases for this problem. The easiest case arises when both A and B are upright rectangles. By upright, I mean parallel to the axis. In this case, the two-dimensional grid problem just becomes two one-dimensional grid problems, because essentially you can solve it separately in the x-coordinate and the y-coordinate, and it's easy. There's a small thing you have to do because there are two coset, whatever. It's easy. Okay. Well, you can see that the grid points in that case line up along vertical lines, but there are two kinds of these vertical lines depending, because every set number is either of the form a plus bi or a plus 1/2 plus b plus 1i plus 1/2 I. So there's two cosets of something and something, but it's an easy problem. All right. Another easy case is when the sets are close to being upright rectangles. I would say that a set is the uprightness of a convex set is just the ratio of its area to the area of its bounding box. The bounding box being the smallest upright rectangle that contains it. If that area is relatively close, then you simply solve first the grid problem for the bounding boxes, and then you simply just check each solution to check whether it's a solution for the original set. And that's efficient if the area is relatively close, because you're only going to throw away some fixed percentage of the solutions. So the runtime per solution to produce is still efficient. Right? Here's another case where it's close to an upright rectangle. And then again, just like in the previous case, the difficult case arises when the sets are very far from their bounding box. So if you have something that's not upright, it's very long and skinny, so the area of the set could be arbitrarily much smaller than the area of the bounding box. And in these cases, you could efficiently enumerate all the solutions of the bounding box, but you would only once in every lifetime might you actually find a point that's in the convex set, right? So suddenly the algorithm is no longer efficient, because we measure efficiency in the runtime per solution produced, right? So this could be exponentially large. In fact, we might never find a solution. So how do we solve this problem? Well, our solution to this problem is linear transformations. More or less just like we did in the one-dimensional case. So think of the plane as R2 now, and not the complex numbers. Right? Then you can have linear 2x2 matrices that linearly act on R2. And certain ones of these matrices have the property that they preserve the ring Z omega. So we call a linear 2x2 operator a grid operator if it goes from this subset of R2, if it's a bijection from this subset of R2 to itself. Okay? So not every operator are grid operators, but there are lots of them. So a 45-degree rotation is a grid operator. This shearing A, which keeps the y-coordinate fixed but moves the points parallel to the x-axis, that's a grid operator. You can check. This is a grid operator. Okay, and there's some others. Okay, and just as in the one-dimensional case, we've got a bijection between solutions. Because if you apply a grid operator to the set A, if G is a grid operator and you apply it to the set A, and you apply the grid operator G bullet to B, by bullet of a matrix, I just mean to take a bullet of each of the entries, then it's clear to see that the solutions to the grid problem for A and B are in one-to-one correspondence with the solutions to the grid problems for G of A and G bullet of B. Right? Because if alpha is in A and alpha bullet is in B, then G of alpha is in here, right? And G bullet of alpha bullet is just a bullet of G of alpha, which is in here. So, and because G is invertible, you can go back and forth. So it's a bijection between the solutions, right? So what we now have to do is, given two sets of the plane that are not upright, find a grid operator that makes them upright, and then just use the ordinary algorithm to enumerate all the solutions. And the fact that this always can be, well, let me first illustrate what we just said, namely, if I apply, let's see what happens if I actually apply this grid operator B. So on the set A, it's a shearing. Actually, it's going to keep the y coordinate fixed, and it's going to move the x coordinate in this direction. Okay, so the set A will sort of be sheared to the right. But to the green set, we have to apply the bullet of this operator. The bullet of this operator has a minus sign here, so the red set will be shearing to the right, and the green set will be shearing to the left in case of the grid operator B. Okay, so you can see that exactly happening. And the important thing, and the grid itself, which is the dual of B, also changes, right? But the set of solutions is invariant because you got 1, 2, 3, 4, 5, 6, 7 of them, and it's the same 7. You know, it's just the B of the other 7 solutions as well. Okay. So now let me just show you this in one of the other windows here. Demo. Okay. So I just want to show you how it's done. Okay. Whoops. Like this. How do I make it? Ah. Good. Sorry. I agree. Right, so now I can start applying grid operators here. For example, a 45-degree rotation, okay, that's the R operator. Sorry about the bad graphics, but it's just how I program it. So this is the R operator, which is a 45-degree rotation, obviously gives the solutions invariant. Now let's apply, for example, an A, okay? A is a grid operator that shears everything to the right, and A inverse is a grid operator that shears everything to the left. This would be A inverse. Whoops. If we so let's try to make the sets upright. Okay, so I'm going to apply R. So 3 rotations. Now it looks like a shearing would be in order. I want the red set to go to the left. I'm talking about above the x-axis, right? I want the red set to go to the left and the green set to go to the right. So what operator would that be? B inverse, right? Let me try B inverse. Okay, let's do it again. I think I got the wrong one of these two, right? So let me try B. Right? So, right, it's getting closer to upright. Okay, maybe I can rotate another time. Apply an A. Oh, whoa, maybe that was not a good idea. Rotate again.
Randomized algorithm.
No, you know, you have to kind of try it for a while. It's like a nice computer game, right? And then you rotate again, another upright. I mean, upright enough anyway, because the red set is now almost fills up its bounding box, and so does the green set, right? Whoa! Yeah, whatever. If I cancel, it's just going to ask me again. Alright, and then, so I just showed you that I can do this, right? Now, a computer program can also do this, and this is really the main technical contribution of our work here. In fact, there is a theorem, which is constructive, which says that if A and B are any bounded convex sets of the non-empty interior of the plane, then there exists a grid operator G such that both these images are 1/15 upright. So it means the area is at least 1/15 of the area of the bounding box. And you can even compute this thing efficiently. And immediately as a corollary, you get the solutions to the two-dimensional grid problems, right? There is an algorithm which, given two bounded convex subsets of the plane, will efficiently enumerate all solutions to the grid problem. Okay? Now that's nice. So that was the math part. Now, this actually has an enormously interesting application for this quantum circuit synthesis that I was talking about before.
So Peter, just a quick question. How are the convex sets given as input to the algorithm?
You just have to give a characteristic function, a way of intersecting the convex set with any line, for example, line whose coordinates are in the algebraic ring, and a bounding box of the convex set. That's sufficient. So then you can just make, that's the information. So that's given as a higher order input to the function. All right. So let's talk about unitary maps that are interesting in quantum computing. So we're interested in 2x2 complex operators that are spanned by these particular generators. The Hadamard gate, that you've maybe seen before, this S gate here, then the scalar omega, which we talked about before, and the T gate, which is 1, 0, 0 omega. So that's called the Clifford plus T group, and it's what everyone thinks when they implement a quantum computer, that's what it's going to have as the built-in gate set. Okay? Now and the reason we can use algebra to reason about this group is because there's this theorem by Klishnikov, Maslov, and Mosca from 2012, which says we can algebraically characterize these things. In fact, U is a Clifford plus T operator if and only if the matrix, and if it's unitary, okay, and the matrix entries are in this ring, which is the Z omega that we were talking about before, except you could possibly divide by some power of root 2. For example, the Hadamard gate does this. Right? Here's an example of such an operator, and then you can, and there's a, and then you can efficiently decompose that into Clifford plus T. It's efficient, and you even know how long this gate sequence is going to be simply by looking at the exponent in the denominator. It's exactly equal to 2k minus 2. Okay? So everything we can say about the Clifford plus T group, we can actually say about algebra. We don't have to talk about circuits at all. So the approximate synthesis problem is, given an operator in there, some arbitrary operator, right, and an epsilon, then find an operator of the Clifford plus T group that approximates it up to epsilon. And we will only do this for Z rotations, because with Euler angles, you can write any arbitrary operator in terms of 3 rotations. So we will just do it for rotations about the Z-axis, which by definition means this sort of matrix here. Okay? And the way we're going to do this is we will approximate it by a matrix of this form. Okay? Now we have, for this to be a solution, we have to make sure 2 things, right? We have to make sure it's unitary. 3 things actually. We have to make sure it's unitary, we have to make sure the elements are from the right ring, and that it's epsilon close to this other one here. Okay? So the problem factors. There's an observation one can make, which is that the error, which is the distance between these 2 operators, actually is only a function of u. It's not a function of t. Because u squared plus t squared is 1, right? And the error only depends on t squared, so it actually only depends on u. That means you can just literally say what region of the complex numbers does the u have to lie in for that to be epsilon close. And the region, it turns out to be one of these convex regions. It's actually just a slice near the perimeter of the unit circle. Okay, so it's close if and only if u lies in this region here. Z is the angle, is the e to the minus theta over 2. Okay, so on the one hand we have to find u inside this region. On the other hand we have to solve a Diophantine equation because we need this thing to be unitary. So we need t dagger t plus u dagger u to be equal to, well, in principle 1, but we've scaled things by a square root of 2 to the k. So it should be equal to 2 to the k. So what we're going to do, but the problem has factored into 2 separate steps. We're simply going to find suitable candidates u, and then for each candidate we're going to try to solve this Diophantine equation, and if we succeed then we have a solution. Okay? Turns out solving Diophantine equations is easy. It's a well-known problem, like Gauss knew how to do that, alright? People before him even. Solving Diophantine equations is easy, but a necessary condition is that the right-hand side has to be, both it and its bullet have to be greater or equal 0, and you have to know a factorization of a certain integer if you want to solve the Diophantine equation. No, thank you very much. Or maybe I'll just let it go there, because then it won't bother me. Okay? So there's an algorithm which can solve this Diophantine equation efficiently, or tell you that no solution exists, provided that we feed this algorithm with the factorization of a certain integer that's a function of u. But that's okay. Factoring integers is hard, but factoring random integers is not very hard. Okay? For example, if you look at 1,000-digit integers, about 1 in 1,000 of them is prime. Okay? So primes you can definitely factor. So if you're given a bunch of candidates and you're asking how long do I have to wait before I find a number that I can factor, you expect to wait about 1,000 candidates before you can factor one. In practice it's a lot less, right? Because numbers that are 2 times a prime or 5 times a prime are also easy to factor, right? So factoring on average is not very hard. Okay. The candidate selection problem is the problem that we sort of solved in this work. So you have to, it turns out, not only do you have to find that u is in this region here, but also u bullet has to be a member of the unit disk. Because that's a necessary condition for the Diophantine equation to even have a solution. Because if a vector is a unit vector, then the bullet of that vector must also be a unit vector. okay, simply because it's an automorphism and the bullet 1 is 1. So, but that's exactly a two-dimensional grid problem, right? I need to find U in one convex set and U bullet in the other convex set. So we've already solved it. So here's the algorithm, right? Enumerate all the grid points using the grid algorithm, which uses grid operators and whatever. Then for each U, calculate the right-hand side, try to factor it. If you can't factor it, try to solve the Diophantine equation. And if you succeed, then you output the U and you have solved the problem. And if you don't, you just move on to the next candidate. Okay, so results. The algorithm described on the previous page is actually optimal. It's going to find the shortest Clifford plus T circuit approximating the given unitary matrix up to epsilon. The absolute shortest, okay? Provided that we have a factoring oracle, which is a quantum computer. Of course, you're not interested in quantum compiling unless you have a quantum computer, so you need a classical computer to compile a classical program, use a quantum computer to compile a quantum program, so that's okay. Right? That's optimal. If we don't have a quantum computer, I just told you that factoring on average is relatively easy too. So it turns out it's still very, very close to optimal in that case. It's optimal plus O of log of 1 over epsilon, which is less than 10 or something. For all epsilon that are of any interest whatsoever. So that's still, even if you don't have a quantum computer, this algorithm is phenomenally close to optimal, especially compared to, say, Solovay-Kitaev, which was the state of the art. Okay? And the algorithm not only computes an upper bound for the t-count by giving you an answer, it also computes a lower bound for the t-count by remembering which integers it couldn't factor, and those could have been possible answers, right? So it tells you sort of how short the shortest circuit could have possibly been, and the runtime is very efficient. So in numbers, for given epsilon, this is how Solovay-Kitaev does. This is the information theoretic lower bound, and this is how our algorithm does in the absence of a factoring algorithm. Right, if you have a quantum computer, it would actually be this column. Right? So you can see that these numbers are very close and very, very much smaller than the Solovay-Kitaev ones. So if you like pictures, this is a doubly exponential scale. So Solovay-Kitaev is a 4th power, so this line has slope 4. All these other lines have slope 1. These other algorithms were optimal, but did this by exhaustive enumeration of all Clifford plus T circuits, so exponential running time, which means you can never go past at 10 to the minus 4 or something like that. And this algorithm, goes to 10 to the minus 2000 even. No problems. And that's the end. Before we have, I just want to, this was the last talk, by the way, so we should have questions, but we should also definitely thank all of the organizers again, and definitely, sing happy birthday or something for Josh. Yeah, so he will sit here.
But let's have questions first.
So let's have questions.
We need to have a question.
Yes. You get the first question.
So you showed duality in fact between discrete and compact groups.
It looks like.
But I mean, I was expecting to see something that looked like Fourier theory, and I didn't see it.
It looks a bit like, right? But it's not. It's only a formal analogy between, how these, it's not a Fourier series at all. But of course, the set and the grid more or less determine each other, right? Because the dual of the grid is dense in the set. But you can't, but no. It's just another kind. I called it duality, but it's probably a little bit cheating, right? It's just an automorphism.
I would push the duality.
Yeah, I mean, there could be an angle there that would be interesting to explore, but right now, I don't know.
Just curious, can you do any of this in another quadratic grid than
Yes, and it's in fact being done. Some of it since after we did this work. So there are other gate bases for quantum computing that people use, like for example the Clifford plus V set, where V is related to the root of 5. Okay, so it's something like 1 over root 5, 1, 2i. This can be useless. 1, 2i, 2i, 1. Like that's the V gate. Okay, so if you do it with that gate, you are in a different ring, but you can use similar methods. And then people have done it, we're now working on the square root of T gate, which is another sort of, so you have cyclotomic integers of order 16 instead of 8. I think all the methods work in that ring as well. And people have done it for the Fibonacci anyons, which are these things that use a topological quantum computing. They're related to the golden ratio, and the matrix is something like phi squared, you know, something with the golden ratio, I think. And that's also been done, not quite the optimal, where you have the grid operators and so on, but people are already within a multiplicative bound, a multiplicative constant of optimal for all these other sort of algebraic fields. So that seems to be a general method that's not just specific to this particular case. Yes?
Your average case algorithm looks, I may be just short-circuited here, but it looks like some algorithms for the modular group and for subtractive GCD algorithms that I've seen. Is there any relationship there?
I have no idea. So it's quite possible that number theorists would have known about all these algorithms, but on the other hand, it was an open problem for 17 years. An open problem in Nielsen and Schwang's book, for example, on quantum information. Whether the exponent even in the Solveig-to-Haiff algorithm could be decreased, say, less than 3. So now we have it to 1. And, you know, so anyway, the point is, there might be mathematicians who already know, you know, these algorithms may have been well known, but they've certainly never been, no one's ever made the connection, for sure. But I don't know if they are, or if they're just similar.
But you're talking specifically about the factoring.
No, I'm talking about subtractive GCD algorithms, average case algorithms.
Yeah.
There's a lot of pieces of what you did that look very similar.
Well, I mean, this, yeah, I mean, roughly what you do is you have a problem of uneven sizes and you reduce it by repeatedly multiplying it by other things.
Yeah.
Similar also to lattice problems and so on,
Yeah.
but usually these problems are hard, so it's surprising that this one turns out to be easy. In fact, it was believed to be hard, right, until we solved it. And this is implemented, by the way, you can generate the circuits. It takes like a few seconds, up to 10 to the minus 2000.